Welcome to our comprehensive guide on network security. In today's digital world, protecting information is more critical than ever. This video will walk you through the essential components of network security, including firewalls, VPNs, IDS, IPS, and SIEM systems. We'll explore how these technologies work together to safeguard sensitive data and ensure the integrity, confidentiality, and availability of your network resources. Whether you're a student, professional, or simply curious about cybersecurity, this journey will help you understand the building blocks of a secure network environment. Let's begin by setting the stage for why network security matters and what you can expect to learn. A firewall is a fundamental security tool that acts as a barrier between your internal network and external threats. It can be hardware, software, or a combination of both, designed to prevent unauthorized access to your private network or individual computers. Firewalls monitor incoming and outgoing traffic, allowing or blocking data packets based on predefined security rules. By controlling network communications, firewalls serve as the first line of defense, protecting sensitive information from cyber attacks and unauthorized users. Understanding how firewalls operate is key to building a robust security posture. Firewalls perform several critical functions within a network. They track and control network communications, deciding whether to pass, reject, encrypt, or log data based on access control policies. Serving as a security gateway, firewalls sit between two networks, typically the internal corporate network and the external internet. By enforcing rules, they help prevent malicious traffic from entering or leaving the network, ensuring only authorized communications are allowed. This scene will clarify how firewalls make these decisions and why their role is so vital in modern cybersecurity. Firewalls come in two main types, hardware and software. Hardware firewalls are typically implemented at the router level, protecting entire networks. They are often more expensive and can be harder to configure but provide robust security for multiple devices. Software firewalls, on the other hand, are installed on individual computers, offering protection at the device level. They are usually less expensive and easier to manage. Understanding the differences between these types helps organizations choose the right solution for their specific needs. The evolution of firewalls has seen significant advancements over the years. Initially, packet filters provided basic filtering at the network layer. As threats became more sophisticated, application proxies and stateful inspection firewalls were developed. Stateful inspection, in particular, brought the ability to track the state of active connections, offering more granular control and improved security. This progression reflects the ongoing need to adapt to emerging threats and protect networks more effectively. Packet filtering is one of the earliest and simplest forms of firewall technology. It operates at the network layer, examining packets based on source and destination IP addresses, ports, and protocols. Packet filters make simple accept or reject decisions without awareness of higher protocol layers. While they are effective as a first line of defense and are commonly deployed on routers, their simplicity means they may not detect more complex threats. Understanding packet filtering is essential for grasping the basics of network security. Packet filters use rules to specify which packets are allowed or blocked. These rules can be based on various fields, such as protocol type, TCP flags, source and destination ports, and IP addresses. For example, a rule might block all incoming packets on port 53 except from trusted DNS servers. By defining logical expressions, administrators can control network access with precision. However, the effectiveness of packet filters depends on the accuracy and completeness of these rules. Configuring packet filters requires a clear security policy and adherence to the principle of least privilege. Administrators should start by allowing only necessary traffic and eliminating any services that are not needed. Each rule set is typically followed by an implicit rule that denies all traffic not explicitly permitted. This approach minimizes the attack surface and ensures that only authorized communications are allowed through the firewall. Let's look at a practical example of packet filter configuration. Suppose you want to allow inbound mail, SMTP, port 25 only to your gateway machine while blocking mail from a specific site called Spigot. By defining rules that specify the source, destination, and port, you can control which packets are allowed and which are blocked. This example illustrates the importance of precise rule definitions in maintaining network security. In another scenario, you may want to allow any inside host to send mail to the outside. This requires a different set of rules, permitting outbound connections to port 25 while still blocking untrusted sources like Spigot. By carefully crafting these rules, you can enable necessary business functions while maintaining a secure network environment. Each configuration decision should be guided by your organization's security policy. Even well-intentioned rules can introduce vulnerabilities. For example, a rule that allows any inside machine to connect to port 25 on an outside machine might inadvertently permit external attackers to access internal systems. This highlights the importance of understanding both the source and destination of traffic, as well as the context in which rules are applied. Regularly reviewing and testing firewall rules is essential to avoid common pitfalls and ensure robust security. To address vulnerabilities, it's crucial to refine your packet filter rules. For instance, restricting access based on both source and destination addresses, and using flags like ACK to distinguish between new and established connections can significantly enhance security. By allowing only specific types of traffic and responses, you reduce the risk of unauthorized access and ensure that only legitimate communications are permitted. Application gateways, also known as proxies, operate at the application layer. They inspect packets in detail, enabling content filtering and more granular control over network traffic. For example, proxies can prevent specific commands such as FTP put from being executed. While they offer improved security, application gateways may have performance and scalability limitations. Their ability to filter content makes them valuable for organizations with strict security requirements. Stateful inspection firewalls represent a significant advancement in firewall technology. They inspect packets between the data link and network layers, maintaining dynamic state tables to track the context of each connection. This allows for more intelligent decision-making, as the firewall can determine whether a packet is part of an established session or a new request. Invented by Check Point, stateful inspection has become a standard feature in modern firewalls, offering enhanced security and flexibility. Network Address Translation, or NAT, is a technique used to convert private internal IP addresses to public legal IP addresses. This process hides the true addresses of individual hosts, protecting them from external attacks and allowing more devices to connect to the network. NAT is commonly used in corporate environments to enhance security and optimize IP address usage. By masking internal addresses, NAT adds an extra layer of defense against potential threats. Deploying firewalls strategically within a network is crucial for comprehensive protection. Firewalls can be placed at the corporate network gateway to filter traffic between the internal network and the internet. Additionally, internal segment gateways can protect sensitive departments like finance or HR from internal threats. By layering defenses, organizations can ensure robust protection against both external and internal attacks, safeguarding critical assets across the network. A virtual private network, or VPN, creates a secure private connection over a public network like the internet. VPNs use authentication and encryption to protect data integrity and confidentiality, making them essential for remote work and secure communications. By establishing encrypted tunnels, VPNs ensure that sensitive information remains protected from eavesdroppers and cybercriminals, even when transmitted across untrusted networks. VPNs come in several types, each serving different purposes. Remote access VPNs allow individual users to connect securely to a corporate network from remote locations using protocols like PAP, CHAP, or Radius. Site-to-site VPNs connect multiple offices over the internet, reducing reliance on leased lines. Extranet VPNs provide business partners with secure access to critical information, while client-server VPNs protect sensitive internal communications. Each type addresses specific organizational needs for secure connectivity. Intrusion detection systems, IDS, and intrusion prevention systems, IPS, are vital for identifying and responding to malicious activities. IDS monitors network traffic for suspicious behavior, generating alerts when potential threats are detected. IPS goes a step further by actively blocking or preventing intrusions. These systems help maintain the confidentiality, integrity, and availability of network resources by detecting and mitigating attacks in real time. An IDS consists of several components, including audit data preprocessors, detection engines, and decision tables. These systems can be deployed as network-based or host-based solutions. Two primary detection approaches are used: anomaly detection, which identifies unusual patterns, and misuse detection, which relies on known attack signatures. By combining these methods, IDS/IPS solutions can effectively identify both known and emerging threats. Security Information and Event Management, or SIEM, is a comprehensive approach to managing security data. SIEM systems collect, analyze, and correlate information from various sources, including firewalls, IDS, IPS, and application logs. By providing centralized visibility and real-time alerts, SIEM enables organizations to detect threats, investigate incidents, and ensure compliance with security policies. SIEM is the backbone of modern security operations, integrating multiple technologies for holistic protection.